So a Turing machine is just a collection of quintuples of that kind. This is a particularly stupid Turing machine that tells whether a number written in decimal notation is even or odd. And what makes it require a program at all is that the machine has to look at the rightmost digit, and it's starting at the leftmost digit. So all these things do is make it move all the way over to the left and then make the determination. Okay. Now, we get from this general so far straightforward idea to Turing's leap to a universal machine. Here's the idea of Turing's universal machine. The universal machine would be a Turing machine. It would have its own table of quintuples, and you would imagine on its tape written up the quintuples of a particular machine written in coded form according to some straightforward code. They could just be the quintuples themselves, say, separated by some punctuation mark, or they wouldn't even need a punctuation mark since they're all the same length, followed by a space, and followed to whatever input you'd want to give that machine. And what it's supposed to do is do exactly what machine M would have done were it presented with that input. What gave Turing the idea that there could be such a machine, and why did he embark on it? Well, he never said, but I can conjecture what he had in mind. Namely, he made this daring leap, and it must have felt very daring and insecure to him at first, that anything that was algorithmic in character could be done by one of these very simple devices. And he said, look, if you give me the code to one of these machines and give me an input to it, I can play machine and do exactly what the machine would do. That's algorithmic. So if I'm right, there ought to be a machine that can do this. And that's a hard test. If it passes, I bet I'm right. That's what I'm guessing was in his head. And so he sat down and he programmed it. And if you look at his 1936 paper, you'll see it's about a page and a half of these quintuples. It's got a few bugs and some problems here and there, but what new program doesn't? But the concept was there. Now I need to say, particularly in connection with something I need to say a little later on, that I'm slightly lying to you because Turing's machines didn't have inputs. What they did was print the digits of an infinite real number. And that's really an irrelevant technical detail which changes almost nothing except, well, you'll see why I bothered to mention it. Well, the next thing that comes to mind is, my goodness, we have one machine which all by itself can do anything algorithmic. You think we could build one like that? Now, there's been the word universality, it truly is ubiquitous because it's thrown around rather loosely. Turing's notion is an abstract one. In particular, it's based on a concept of computation in which there are no worries about space or time. The tape is infinite. It can have as many symbols as you want on it. And with that simple instruction code, all this can do is deal with one symbol at a time. Any substantial computation will involve an enormous number of steps. So the question of whether you can realize this notion or something like this notion in a useful physical object is by no means established by this, but it certainly suggests that one should try, and the evidence is that it was in Turing's mind from the very beginning that one should try. While he was here in Princeton in the old fine hall, the same place I was when I was here in Princeton, it was next door to the Palmer Physics Lab with just a short corridor going over to it, and he went over there and got to use their machine shop, and he built himself a binary multiplier, which is an indication of what he had in mind. Meanwhile, of course, the Second World War intervened. He did his heroic work involving decryption of the German codes, as is well known. It's worth remarking that that he designed this machine that was called I don't know how to pronounce it, Bombe, B-O-M-B-E, that did a logical analysis of incoming Enigma traffic, Enigma being the machine that the German used for naval communication. This was basically a logical machine that that looked for possible decryptions of a particular message based on what was already known about it. The Germans were pretty slipshod. The politics said every message had to end with Heil Hitler, for example. But still, the machine was sufficiently complex that the hints that they had to begin with was certainly not enough. There was still a very large number of possibilities, and these bombers would sift through all the possibilities until they found one that worked. And the remarkable thing about this machine was that Turing designed it, he gave it to the engineers to build it, and it worked right out of the box. By the end of the war, there were hundreds of them on both sides of the Atlantic. The war was over, and Turing was dead set on building a real computer which would approximate universality as much as possible. He called the machine the ACE, for Automatic Computing Engine, and he wrote a report. He got a job with the National Physics Laboratory in England and wanted to use that as a base for getting his machine up and running. He wrote a report in which he had complete descriptions, circuit diagrams, cost estimate. It was going to cost £11,000 to build the whole thing. And in the flush of optimism about it, he gave a lecture to the London Mathematical Society in 1947 in which he tried to tell his audience something about what he foresaw about the machine. It's very interesting to read that ACE report and compare it with the engineering literature of the day, because it's ahead of its time in all sorts of ways. For example, the idea of using a stack for subroutine calls was right there. He didn't. We say push and pop. He said bury and unbury. And his list of things that the computer might be expected to do included a great deal more than what one would think of as number crunching. There was a great deal of, for example, he mentioned playing games, for example. Chess was very much on his mind as a long-range possibility. This slide, which you've probably read by now, is quoted from that talk, and it continues in the next slide. What I want to emphasize, his emphasis that it was essential for the abstract universal machine that the memory be infinite. In fact, he goes on to say, it's not in the quote here, that with a finite memory, nothing non-trivial can be done. It will eventually repeat. It'll be periodic. So the infinity of the memory. But what he took from that is that the ACE can be regarded as a practical version, and they all have to have a very extensive form of memory. The memory needs to be large. And now here he describes in a few simple words what makes the universal machine be universal. We punch a description of the machine we wish to imitate on the tape of the universal machine. And the digital computing machines are practical versions of the universal machines because appropriate instructions for any particular problem are just stored in the memory. So it's all laid out right. It's all laid out right there. Whoops. Sorry. Okay. To emphasize this point, which I think is really crucial, is that what is it that enables something that we might call universality, strictly speaking, approximate universality is what one should say. Is it a rich supply of basic operations? Well, my goodness, the abstract Turing machines have this tiny skeletal collection of operations. It's infinite memory. And so the engineers and the mathematicians advising them in those years started looking for a physical realization of what in those days passed for a very large memory. There were two candidates that presented themselves. The one that was first in line and that both Turing and von Neumann made use of in their first designs were acoustic delay lines. This these things actually work, though I find it very hard to imagine that they do. The data is stored in the form of an acoustic wave in a tube of mercury, and the wave bounces up and down the tube, and you write and read from the top of the tube, and the programmer, if the programmer is going to write efficient code, has to be cognizant enough of the behavior of the tube as to catch the data needed when it's near the top. Otherwise, the program sits and waits for it to come to the top. The second medium, and the one that I became personally familiar with as a programmer, were electrostatic storage on cathode ray tubes. Well, what used to be called television tubes until a few years ago, except that these were little ones, and you would have an array of dots and double dots that could be zeros and ones. The machine built at the Institute for Advanced Study, and its a brother at University of Illinois that I learned to program on used 40 of these tubes with 1,024 bits, 32 by 32 array on each tube. It had its weirdness for the programmer too, which I learned the hard way. This was called the Williams memory. It was thought at first that very special tubes would be needed, but then Williams, who a gifted engineer, worked out a way of using off-the-shelf cathode ray tubes. Again, this is something that's hard to believe would actually work. The problem with the electrostatic storage is the electrons don't stay there; they just fade off. What Williams worked out was a system where the alternating with computation steps, there would be read-around steps in which the contents of a piece of the memory would be read and rewritten, so it was always kept fresh. And again, this had a message for the programmer. If you wrote a program with a very tight inductive loop, you would hit the same memory location over and over again, and charge would splash over and interfere with the neighboring bits. I wrote such a program, and found out about it the hard way. Now, it took a long time. The extent to which what Turing had done and what von Neumann picked up on, the extent to which this was a real shift in thinking, is very hard for people to understand, because the new way of thought became so familiar and natural they quickly forgot about it. Here's an example of a man who didn't forget. Howard Aiken was a pioneer of calculating machines. He was involved with the Mark I at Harvard, and as late as 1956 he made this remarkable statement. It should turn out the basic logics of a machine designed for the numerical solution of differential equations coincide with the logics of a machine intended to make bills for a department store. I would regard this as the most amazing coincidence I've ever encountered. Of course, in 1956, he could lease a machine from IBM that would do would do exactly that. Another example that indicates the shift in the way people were thinking about computation is the issue of whether to use binary or decimal arithmetic in the design of a computer. There would be the debates, there were actual debates about this along the lines of, well, it's true that if we do the arithmetic in binary, it'll all be more simpler circuits, it'll be more efficient and so on. But then we're going to have special extra machinery because our users aren't going to want to use binary, they're going to want to do decimal. We're going to have special machines to translate back and forth between binary and decimal. You can even see a trace of this in Turing's ACE report, where he actually includes as one of the things you have to include in the design of the machine, this capability of translating back and forth between binary and decimal. But then he explained that it really isn't a separate gadget, but I better include it so you won't think I left it out. That the revolution can be expressed in the phrase, it's all data, you know, and things that were thought of as entirely separate categories were really all the same thing, depending on what point of view you took. Von Neumann was very strange in his attitude toward Turing. Some of that was mentioned in some of yesterday's talks. Here comes von Neumann, on the one hand, telling you that, yeah, he knows what Turing did. That's what the first sentence says. Yeah, I know what Turing did. But that's not really the crucial point. The crucial point is practical stuff, and then what he says is true enough. You need to think about what kinds of problems you want and what are the best basic instructions. In fact, Turing and von Neumann in effect disagreed pretty sharply about what the best instruction set to have. Von Neumann was really interested in number crunching, and so he wanted fast multiplication, floating point multiplication, things like that built in to the basic architecture of the machine. Turing was very much a minimalist, I guess partly influenced by his abstract computer, which was as minimal as you can get, but partly because he was interested in problems of a logical character as well as numerical character, and wanted a machine that was better balanced on both. Von Neumann did write what in a sense was the first modern computer program, a merge sort program to run on the Ordvac, and he explained that by doing that, I guess I haven't mentioned EDVAC before, I'm sorry. The EDVAC was the machine that von Neumann was proposing be built at the Moore School in Philadelphia, which, like the ACE, would have memory based on these acoustic delay lines. And he was very pleased that he was able to write a fast sort program on the EDVAC, and said that he used the word all-purpose, that it shows that the controls are balanced and the machine is essentially all-purpose. The, von Neumann's reaction to Gödel's incompleteness has already been mentioned, and it certainly marked him in a very strong way. I mean, he was this absolutely brilliant young man who was captivated by David Hilbert's program for proving the consistency of arithmetic. He worked very hard on it. He actually published a paper on it which didn't prove as much as he thought it had. But then when they were sitting around the table at this meeting in Königsberg in 1930 that was mentioned yesterday, he discovered that he'd been wasting his time. But he was very excited by what Gödel had done, got up and talked to him about it, and then he went home and thought about it and managed to prove what we know as Gödel's second incompleteness theorem, the unprovability of consistency. And he wrote Gödel a letter about it, and Gödel wrote back, said, yes, I know, and sent him the manuscript that had already been submitted for publication. After that, von Neumann boasted that he never read another logic paper. His collaborator, Goldstein, tells a story about a dream that von Neumann had, which von Neumann told him. He obviously would not have known about it any other way. I think it's very telling. Von Neumann said that while he was working on the consistency problem, he had a dream in which an obstacle he was facing seemed to melt away. And the next day he thought about it, and it was a hint, and he worked and worked, but there was still an obstacle. That night he dreamt again, and again he thought that he had made progress. The next day was that meeting in Königsberg, and he said, Gödel's very lucky that I didn't dream a third night. This is something I wrote on the it's all data point. Before Turing, the supposition was that the three categories, machine, program, and data, were separate. There was hardware, there was input, but the Turing machine had all of these things at once. And of course, this fluidity is crucial to computer science. The program looks like data to the compiler. This is the book from which that quotation came. It was written, it first appeared in the year 2000. This is the current Turing Centenary edition, which is basically the same book with some rather minor updates. I should explain something of the history. I started writing about Turing's contributions to modern computation in the 1980s. At that time, Turing's name was hardly mentioned at all. If you looked in the annals of the history of computation, you saw a big fight about whether the credit for the stored program concept, as it was called, belongs to von Neumann or to the engineers Eckert and Mauschly. Turing's name didn't appear at all. Partly, by the time I was writing this book, its original edition, the atmosphere had changed totally, and Time magazine was including Turing in his list of the top 20 thinkers of the 20th century, with von Neumann given a mention as somebody making use of Turing's ideas. So I was rather startled to get the following in the mail. When I first saw this, I thought, oh great, somebody's written a sequel to my book. I was going from Leibniz to Turing, he's going from Turing to Dijkstra. And in many ways, this is a wonderful book. It has these interviews with these 4 Turing Award winners are very well done and very interesting. We're going to hear from Barbara Liskov this afternoon, and I don't know why he doesn't mention, why Dijkstra isn't mentioned in that. I guess Dijkstra never won a prize, that's why. But the interview with Dijkstra is really I think is really the best thing in the book. But the book is an attack on me. Now, it isn't necessarily bad for a scholar to be attacked. It's bad to be ignored. For example, he complains that these very concepts, hardware and software, simply did not exist at the time. Well, the words didn't exist, but the concept certainly did. People knew what a machine was, and they knew you had to program the machine. Maybe you fed it punch cards. Maybe you connected tapes into a plug board, but you certainly programmed it, and you certainly input data to it. The other thing he was annoyed by was that Turing's original machines were printing real numbers rather than computing functions. He mentions for Dijkstra was interested in the unsolvability of the halting problem, and he says that the halting problem is really not Turing's. It's Martin Davis and his computability and unsolvability. Well, Turing had something called the circle-free problem, which wanted to be the halting problem, but didn't quite make it because of the technicalities of a first draft. It's of too high a degree of unsolvability. It's a degree 0 double jump for people who knows it. But the printing problem, which is next door to the halting problem, is right there in Turing's original paper. So I don't know why he is so mad. He really wrote a nice book, but I wanted to talk briefly about the differences between Turing's ACE and von Neumann's EDVAC. As I indicated, Turing was interested in logical problems, and von Neumann was interested in number crunching. Particularly, the first thing he set the Institute machine on was a computation for a hydrogen bomb. So And I like this quote. Turing didn't know that he was never going to get anywhere at the National Physics Lab because of bureaucratic inertia of various kinds. He was used to the situation at Bletchley Park when they needed something and weren't getting the supplies they needed, and the military brass were bothering them. He shot off a letter to Winston Churchill, who quickly wrote back saying, "Give these people everything they need." This didn't happen in peacetime. And he eventually left before the ACE was built. There was a smaller version, the Pilot ACE, which was built and worked, and a commercial version of it called the Deuce was actually built and apparently did some useful work. When I gave a talk on Turing at Manchester a couple of years ago, I met somebody who had actually programmed the Deuce in Australia, so they did exist. In any case, Turing's attitude is very much indicated by this quotation. It's very contrary to the line of development here, and much more in the American tradition of solving one's difficulty by means of much equipment rather than by thought. Furthermore, certain operations which we regard as more fundamental than addition and multiplication have been omitted. He actually was going to do that by coding. I like to compare the two to the controversy in a much later time about CISC versus RISC chip architecture. It's basically the same argument. Somebody told me how you should really read RISC, not reduced in different sets, but I don't remember. Something about leaving the interesting things to the compiler, but I can't say it right. Strange thing about this notion of universality, there are people who, for some reason, want to make a claim of universality for pre-1947 devices, real or imagined. Our wonderful Robin Gandy bothered to point out that Babbage's machine would do anything algorithmic if you gave it an infinite memory. Of course it would. I mean, Turing had already shown, as Robin perfectly well knew, that just moving one symbol would do it. I heard a talk by Benjamin Wells a couple of years back in which he claimed the Colossus, which was an electronic device used for encryption at Bletchley Park, decryption, I'm sorry, at Bletchley Park, was universal. The ENIAC was claimed to be an all-purpose machine. The ENIAC was an engineering marvel as managing to make 15,000 hot vacuum tubes all work usefully at the same time, but it was a total logical mess. For example, there was a whole unit of it which was a digitized differential analyzer. Its order code was over the top and its memory was minimal. It was exactly the opposite of what an all-purpose computer ought to be. This Rojas wrote a paper saying that Konrad Zuse was a German pioneer with computers, that his Z3 was really universal. Konrad Zuse was a remarkable man. During the Second World War, he tried to interest the German government in what he was doing, and was was making relays by winding the coils himself with himself and his helpers. But his order code didn't even have a conditional jump. If you could have, it was strictly straight line code. And Edgar Daylight, the author of the book I mentioned, claimed that Aiken, of all people, that his machine was universal, even though, as we saw, and as Daylight knows perfectly well, Aiken said there can't be a universal machine. It can't be a machine that can do differential equations and bills for a store at the same time. So I have no idea. Time is disappearing. I want to make some quick remarks about artificial intelligence in relation to universality. Before I say that, one quick thing I should have said earlier is that I've emphasized space, but time is just as important. And of course, the ability to use electronics so that basic operations happen fast is just as important as having an infinite, as having a large memory. It wouldn't do you much good to be able to calculate something if it took longer than the lifetime of the galaxy for the number to come out. There's been people argue about whether artificial intelligence is possible or not, and the argument takes various forms, but as far as I know, and I may be wrong about that, I don't think anybody has just sat down and talked about what the basis for the idea that this inert thing, the computer, should be capable, should even be thought of as being capable of anything like intelligence. And I would say that the basic underlying assumption are these two assumptions. The first is that the human mind is a function of the brain, and the second is that the brain is really a computer. And you may, the truth is that neither of those things is a solid fact at this point. The one is probably more plausible than two, but if you believe both of those, then there's no reason not to imagine that a computer might not be able to do what the brain does, and that's the basis for that's really the basis for the whole field. Now, if you reject the possibility, you really should reject one or two, and some people do. Roger Penrose believes one, but not two. He thinks that he has this argument based on Gödel incompleteness, which I'm running so short of time, I'm not going to stop to explain that, but he's written 2 books, and logicians try to set him straight, and he doesn't listen. Gödel believes 2, but not 1. Gödel believed 2, but not 1. He was a Cartesian dualist. He thought that the mind had an existence separate from what the brain does. But as far as he was concerned, the brain looked to him just like a Turing machine. So it goes. I'm going to skip Searle, who philosopher at Berkeley, who invents parables that don't make a lot of sense. I'll just skip it. I want to make one last. I want to make one last comment. And this, with making this takes an enormous amount of what in Yiddish is called chutzpah. Was I don't know anything about DNA, and there are plenty of people in the audience who know a lot about it. But when I look at DNA, I see a Turing machine tape. And I have this idea that somewhere in the machinery of living cells is a command processor, and that somewhere along in the non-coding parts of the DNA, particularly parts that are conserved by evolution, is code, which is being processed by this code, and that works to speed up evolution in an important manner. It's entirely safe for me to make a comment like this, because if it, as is most likely pure foolishness, it will be forgotten. And if it turns out to have a kernel of truth to it, people will think I'm enormously clever. Okay, I'll stop it there.
Hi. Thanks very much. Very enjoyable talk. My name is Arch Davis. We're probably unrelated, but in the early 70s, I was in the basement of the Newfine Library and pulled out a manuscript that von Neumann had written, in which he said that he was very frustrated with the Williams tubes and the things they would do that were not digital. And so he said, memory will never be successful until we can print it like we print books. And that was 25 years before photolithography was. I'm sorry,
who made this comment and when?
John von Neumann. I saw a paper that he wrote. It was a manuscript, if I remember. It was in handwriting, and where he said that that you have to print memory like books before it's really going to be successful. And I thought that was very ahead of its time. I also had my hands on a UNIVAC 1, which had mercury delay lines in it. The first commercial computer in the world was installed in 1954, General Electric, and it was used for some kind of bookkeeping. As I understand, that thing stayed in service until 1980. Can you imagine that today, that longevity?
That's amazing. Did you write code for it?
No, I did. I walked inside it and played with the tapes. Yeah. They weren't infinite, but they were metal. They were metal tapes. You could actually read the bits with a little developer fluid that was finely divided iron. You could put on the tape, and you could read the bits off with a little magnifying glass. Wasn't a lot of density, but the thing ran, if that's correct, for 26 years, and did something useful for General Electric. But so thank you again.
I have a question over here. Is there anything that you know of in the literature that would indicate whether Turing had thought about or proposed anything relating to either network or parallelism? Because with a very long tape, you could obviously imagine it running between his little engines and over very long distances.
So you're asking whether Turing wrote anything about parallelism?
Or whether you know of anything that people attributed to him about networking, namely the ability of machines to interact, or parallelism, namely multiple machines to simultaneously cooperate on a given task.
No, I guess I don't.
Okay. Thank you.
So you stressed the importance that he put on the infinite tape. Was there ever any hint in his writings that he appreciated that there would be different problems you could solve with different finite amounts of memory? So was there any sort of notion of kind of, you know, a complexity hierarchy based on how much memory you had?
Not that I'm aware of. Yeah.
You put up a list of non-universal machines, and I want to see if I understood your argument. Were you saying none of these were universal machines, or were you saying some of these, in fact, were universal machines? The analytic engine was a universal machine, but Babbage didn't know it. So
No.
is the point Turing was the first person who made a universal machine?
I was obscure.
Or the first who did it and knew
I
it?
was saying that without these, none of these machines had a large memory. None of these machines had a large memory. So what these people who claimed universality for them were saying is if you added a very large memory to these machines, they would be universal. And I said, sure, but that's not the point. The point is that they didn't have a large memory. I'm sorry I wasn't clearer.
But then what exactly is your argument? If it's not universal till it has an infinite memory, I don't think we have one of those yet.
Well, we approximate. And it's certainly true that as the memories get bigger and bigger, the more wonderful things, you know, we're able to do. And the speed, too. Yeah.
I guess.
So there's one paper by von Neumann, which was not a number crunching paper, in that it was his construction of self-replicating machine. Now,
That's true.
Which Dyson, in his Disturbing the Universe, pointed out was actually had the basic ideas of the DNA, the modern idea of a cell. But if my memory is right, didn't he use universal machine by Turing to construct it? Is that
No,
true?
not particularly.
You don't know?
No, I don't think so. It was done very beautifully by von Neumann, but the basic idea is really already there in Kleine's recursion theorem.
Martin, great talk. I really enjoyed that. I have to say, when you put up the book that attacked you, it's Edgar Daylight. It took me a couple of seconds to realize that it wasn't some kind of license plate like anagram for Edgar Dijkstra. You know, where you use different letters to represent others. So, anyway.
One more question.
On this point that we were just talking about, I just want to make sure, because I want to go away understanding what you were meaning to say. I believe what you're trying to say is the ACE machine, in some sense, was the first universal machine because Turing understood the importance of infinite memory towards universality, and he wanted a large amount of memory for that purpose. In other words, the others could have had, they all had finite memories, but the difference was that Turing, when he designed ACE, understood the importance of infinite memory.
They had big memories, and they knew that they were going to use the memory to put put descriptions of algorithms into the memory along with the data. He says it, you know, very clearly in something I had on the screen toward the beginning of the talk.